All right, so conservation of momentum just means that momentum doesn't change. So if we take some situation and we add up all the momentum before and all the momentum after, the total momentum is going to be the same. And that's the cool thing about momentum. Let me just give you an example. Let's imagine that you've got a cart, right? And maybe it's moving along like this, and you run. Saw somebody do this. They threw their skateboard on the ground in front of them, and then they ran, and then you run, of course, a little faster than it, right? And then in the end, this kid's standing on the skateboard, right? I was very impressed by that, right? Well, the skateboard's going a little slower. You're going a little faster. In the end, you're going to be going a little bit slower than you were, especially if the skateboard has substantial mass, right? But what conservation of momentum says is that if I add up this momentum, then m times v plus m times v is going to equal m plus m, because you both have the same mass, times v. Whoops, that's a v. Okay, that's what we say. When we say it's conserved, we mean that if we add up all the momentum before, it's going to equal the momentum after. Okay. Now, let me just show you why this is. Imagine that you have a system. You have this is supposed to be two people in space, right? Spaceman A and Spaceman B. Okay, it's been interpreted various ways, right? But let's imagine that let's imagine that Spaceman A pushes B this way, right? Okay. The change in momentum of B is going to be the force that A exerts times some amount of time, right? Okay. Now, what you got to understand, though, is that the forces exist in equal and opposite pairs, right? So if A pushes B, there's a force on A, right? And that's the force that B exerts on them, times the same amount of time, right? Okay, and then, of course, force B just equals the opposite of force A. This is Newton's third law. Newton's third law, right? Okay, says that the force B is the opposite of force A, right? And so that means that I can just substitute minus FA for that, right? Right, that's the change in momentum of object A. And then if we add the change in momentum of object B, this will always add up to 0. It doesn't matter how many objects you have, okay? Because all objects interact with forces. The forces exist in equal and opposite pairs, and they cause equal and opposite changes in momentum. And so momentum is something that cannot be changed. And it's a vector, so that makes it maybe a little harder than energy in that way, but it's easier than energy because it's so easy to calculate, right? Momentum essentially is just m times v. Anyway, look at the examples. I think if you look at 4 examples, you'll know how to do it. Yeah.